Hello students, welcome back to another session of Econometric Methods course. In our earlier session, we saw certain concepts quite essential for the econometric analysis in statistics. In continuation to that session, we are today going to see the theoretical distributions that are quite often used in the econometric analysis. These theoretical distributions are quite essential in the statistical inference. We already saw how a random variable will be associated with a probability density distribution. Here we are going to see some of the common probability distributions, probability density distributions we use in econometric analysis. In today's session, we are going to see some 4 prominent sampling distributions. The first among them is normal distribution. This distribution was first proposed by Frederick Gauss, and so in his name it is called Gaussian distribution. The normal distribution and those derived from it are the most widely used distributions in statistics and econometrics. Assuming that random variables defined over population are normally distributed, simplified probability calculations. Statistical inference in econometrics is mostly relying on the normal and other related distributions, even when the underlying population is not necessarily normal. A normal random variable is a continuous random variable that can take any value from minus infinity to plus infinity. Its probability density function has the familiar bell shape graph we are going to see. Mathematically, the probability density function of a random variable x can be defined as f of x is equal to 1 by sigma square root of 2 pi exponential minus x minus mu whole square divided by 2 sigma square, where x vary between minus infinity to plus infinity. Here mu is the expected value of x and variance is the variance of x. Here it is denoted by sigma square. We say that x has a normal distribution with expected value mu and variance sigma square, and this is written as x follows normal with mu comma sigma square. Because the normal distribution is symmetric about mu, mu is also the median and mode of x. Let us see some properties of normal distribution. Normal distribution is a family of distributions. Each of them have these properties. The total area under the curve is always 1. 2, the curve is symmetrical so that the mean, median and mode fall together or stays together or coincides together. The curve is bell shaped. The greatest proportion of frequencies lies close to the mean. The further from the mean one goes in either direction, the fewer the scores or probability or frequency. 5, almost all the frequencies, that is 0.997 of them lie within 3 standard deviations of the mean. It is important to note normal distribution is determined by mu, the mean of the population, and sigma, the standard deviation of the population. The value of the mean fixes the location of the normal curve where it is centered. In all the normal curve, half the probability lie to the left of the mean and half to the right. The value of the standard deviation determines the spread. The bigger the standard deviation, the more spread out or flat the curve. You can see the diagram in this regard. I have shown two normal curves with different standard deviation, one having the flatter, the other one having the steeped standard deviation. For instance, let us see the two normal distributions represented in the diagram. The first normal distribution, which is represented in your left, is having a standard deviation sigma 1, which is steeper, and the second one, which is in the right hand side, having the standard deviation sigma 2, which is flatter. Naturally, sigma 1 is less than sigma 2. Now, let us see the standard normal distribution. One special case of normal distribution occurs when the mean is 0 and the variance, consequently the standard deviation is unity. If a random variable z has normal distribution with 0 mean and 1 standard deviation, then we say it has a standard normal distribution. The PDF of a standard normal random variable is denoted by phi of z with mu 0 and sigma square 1. It may be given as phi z is equal to 1 by 2 pi exponential minus z squared by 2, where z varies between minus infinity to plus infinity. Now, look at the diagram which represents the standard normal distribution curve. It is a bell shaped curve having mean at the center, that is no 0 here, 0 mean it has, and if you see the distribution, the probability lying between minus 1 sigma to plus 1 sigma of z is about 68% of the probability. If you take the probability area between minus sigma to minus 2 sigma to plus 2 sigma, you will have about 96% of the probability. In the case of minus 3 sigma to plus 3 sigma, you have got about almost 99% of the probability lying within this region. Now, let us see another critical diagram. The diagram shows the usual area. Here you can see the shaded area in your right side standard normal distribution curve, which is the probability, and if in your left side probability distribution curve, you can see an area that we will usually call it the critical region. The critical region is very important in your inferential decisions. For instance, the 95% of the confidence 95% of the confidence interval, the critical value is 1.96. The 99% of the confidence interval, you have the critical value 2.575. Now, let us see the chi-square distribution. The chi-square distribution is obtained directly from independent standard normal variables. Let zi, that is I varies from 1 to n, be independent random variables, each distributed as standard normal. Define a new random variable as the sum of the squares of the z. Let me define chi-square. This is the symbol, this is a Greek symbol used to represent the chi-square distribution. Chi-square is equal to sigma I varies from 1 to n z square. Chi-square has what is known as a chi-square distribution with n degrees of freedom, or df for short. We write this as chi-square subscript n. The df in the chi-square distribution corresponds to the number of terms in the sum. The concept of degrees of freedom will play an important role in our statistical and econometric analysis. The PDF for chi-square distribution with varying degrees of freedom is given in the following diagram. Look at the first diagram. The curves with different degrees of freedom is given. The chi-square probability density function with different degrees of freedom is given in this diagram. Just look at that. For the degrees of freedom 1, that is df1, the curve is almost like a rectangular parabola, and otherwise it is getting flatter and flatter as the degrees of freedom increases. This is the degrees of freedom which is used to identify the curve on which we need to find the critical value. So, the degrees of freedom helps us to identify the curve on which we have to see the critical value. It can be shown that for chi-square with n degrees of freedom, the expected value is n, that is the number of terms in the summation, and the variance is 2n. Let us see some of the properties of chi-square distribution. Chi-square is non-negative in value, it positively valued because all discrepancies are squared. Both positive and negative discrepancies make a positive contribution to the value of chi-square. 2. Chi-square will be 0 only in the unusual event that each observed frequency exactly equals the corresponding expected frequency. 3. It is not symmetrical, it is skewed to the right as mentioned earlier. The reason for this is because all the values are positive, and hence so instead of having a symmetrical distribution, we have a distribution on the positive side. 4. Since density function chi-square does not contain any parameter of population, chi-square test statistic is referred to as a non-parametric distribution. This chi-square distribution does not depend upon the form of the parent population. 5. There are many chi-square distributions. As with the t distribution, there is a different chi-square distribution for the value of each degree of freedom. Now, let us see some of the uses of chi-square distribution. To find out the confidence interval for population variance of a normal distribution, this is used to test the hypothetical value of the population variance. 3. It is used to test the goodness of fit in the case of the regression analysis. It is used to evaluate the overall fit of the regression model. 4. It is used to test the independence of attribute. 5 or 5th, it is used to test the homogeneity of independent estimate of the population variance. 6. It is used to test the homogeneity of independent estimate of the population correlation coefficients. Okay, now let us see some of the characteristic features of t distribution. 5. Chi-square distribution is used to test the homogeneity of independent estimate of the population variance. 6. Chi-square distribution is used to test the homogeneity of independent estimate of the population correlation coefficients. Now, let us see some of the features of t distribution. If x follows a normal distribution with 0 mean and sigma square standard deviation, sigma square variance, and y follows a chi-square distribution with n degrees of freedom, and x and y are independent random variables, then z is equal to x divided by y divided by n has a t distribution with degrees of freedom n. In the regression model, n is derived from the number of observations and number of independent variables used. We write this z follows t with subscript n. The t distribution is a symmetric probability distribution like the normal distribution, but is flatter than the normal and has the t distribution as follows. Let us see the following diagram. It shows the t distribution curve. The t distribution is symmetric probability distribution like the normal distribution, but is flatter than the normal. You can see from the diagram, as the degrees of freedom increases, the curve goes steeper and steeper. So, as the degrees of freedom decreases, the curve is flatter and flatter. The t distribution is a workhorse in the classical statistics and in multiple regression analysis. We obtain a t distribution from a standard normal and a chi-square random variable. Let Z have a standard normal distribution and let X have a chi-square distribution with n degrees of freedom, and both are independent. Then the random variable can be defined as t is equal to Z by square root of x by n. In a regression model, as we have already seen, the regression coefficient beta has got follows t distribution. In this case, t is equal to beta divided by square root of estimated sigma hat divided by n minus 2, that follows t n minus 2. This distribution, actually this statistic is used for testing the significance of the regression coefficient. Now, let us see some of the properties of t distribution. 1. Like standard normal distribution, the shape of the student distribution is also bell shaped and symmetrical with mean 0. 2. The t distribution ranges from minus infinity to plus infinity. 3. The shape of t distribution changes with the change in the degrees of freedom. 4. It is less peaked at the center and higher in tails, thus it assumes platic curtic shape. 5. The t distribution has a greater dispersion than the standard normal distribution, and as the sample size n increases, it assumes the normal distribution. Here the sample size is said to be large when n is greater than 30. Let us see some of the uses of t distribution. T distribution is used to find out the confidence interval for population mean of a normal distribution when unknown population standard deviation. 2. It is used to test sample mean x bar differs significantly from the hypothetical value of the population unknown standard deviation when population mean is mu. 3. The t distribution is used to find the significance of difference between two population means when the population standard deviation is unknown. 4. To test the significance of correlation coefficients and regression coefficients. As usual in the econometric analysis, this use is very important. The standard t distributions are used for the purpose of testing the significance of those regression coefficients. Now, let us see some of the features of F distribution. If Z1 follows chi-square distribution with n minus 1 degrees of freedom and Z2 follows chi-square distribution with n2 degrees of freedom and Z1 and Z2 are independent, then y is equal to Z1 by n1 by Z2 by n2 has F distribution with degrees of freedom n1 and n2. We write this as F y follows F subscript n1, n2. In addition to the normal distribution and the derived distributions like chi-square, t and f that are commonly used, now let us see the properties of f distribution. 1. The f distribution is positively skewed, and with the increase in the degrees of freedom V1 and V2, its skewness decreases. 2. The value of f distribution is always positive or 0, since the variance or the square of the deviations and hence cannot assume negative values. Its value lies between 0 and infinity. 3. The shape of f distribution depends on its parameters V1 and V2. Here the V1 is the degrees of freedom of the numerator and V2 is the degrees of freedom of the denominator. 4. The value of the area lying on the left hand side of the distribution can be found out by taking the reciprocal of f values of the right hand side, and the degrees of freedom in the numerator and the denominator are interchanged. This is called as reciprocal property of f distribution. 5. This property is mainly used in the situation when the values of the lower tail f values are to be determined corresponding to the upper tail f values. Thus, these are the properties of f distribution that tells how the sample is distributed under study and what statistical inferences can be drawn from them. Now, let us see some of the properties of f distribution. 1. F distributions are used to test the equality of two population variances. 2. F distributions are used to test the significance of an observed multiple correlation. 3. F distributions are used to test the significance of correlation ratio. 4. F distributions are used to test the model fit or linearity of regression. 5. The F distribution is used to test the equality of several means. So, in regression analysis, this is used to test the fit of the regression model. Okay, let us now summarize what we had studied so far. Today we saw some of the prominent sampling distributions used in the statistical inference of regression analysis. I hope you would have enjoyed this session. Thank you.